as we continue working with linear equations and functions, we're going to talk about solving systems of linear equations. And in short, a system of linear equations is solved at their intersection point. And there are three types. When we're thinking about our equations, we know that parallel lines have the same slope and they never touch. And if they have anything other than the same slope, we know that two linear equations will intersect somewhere on the coordinate plane. So just remembering that, we should be able to look at this first example where it's solving a system of equations by graphing. And it says, what is the solution to this system? Use the graph. So it's going to be where that system connects or overlaps or touches, or however you want to think of it in those terms. So if I go ahead and graph these, I can create a table of values, or I know that I should be able to take this first equation, which is y equals 2x plus 4, and my slope is going to be the 2, which is 2 over 1, rise over run, and my y-intercept should be equal to 4. So I can go ahead and start at, let's see, I didn't do any numbering over here on my graph. So let's see, that should be, once you go ahead and do your spacings on your graph, you should be able to do some graphing at that point in time. So let me see here. So I've updated my intervals. I just said spacings, but I'm at intervals of my coordinate plane. I have y and I have x. And I go ahead and start at my y-intercept of 4, which would be 1, 2, 3, 4. And then my slope is going to be up 2 over 1. So it's either going to be up 2 over 1 or it's going to be down 2, back 1. So up 2 over 1, up 2 over 1, probably somewhere up there. Down 2 and back 1, down 2 and back 1. And I'm just going to keep doing that slope. And now in order to graph this line, I want to make sure that I connect all my points or my solutions of this line. All right, so there's one graph, and the next graph is going to be y equals x plus 2, and my y-intercept here, my y-intercept is going to be positive 2, and then my slope is going to be the coefficient of x, which is 1. So I am looking at 1 over 1 or negative 1 over negative 1. So starting on my graph at y equals 2, I'm going to go up 1 over 1. So up 1 over 1, up 1 over 1, up 1 over 1, back 1, down 1, back 1, down 1, back 1, down 1, back 1. And as I connect this, continuing my line, we'll see that my connection, my intersection point, my overlap is going to be at, let's see here, negative 2 and 0. That's where those two sections intersect, so that would be the solution. And I've graphed it, but if I wanted to understand that mathematically, if I went ahead and replaced y equals x plus 2 with that ordered pair, if I replace x and y, I would have 0 is equal to negative 2 plus 2, and that would be 0 is equal to 0. So yes, that is a solution for that equation. And then if I take, and I have y equals 2x plus 4, and I take, I think I did say y, and y equals 2x plus 4, if I replace y with 0, 0 is equal to 2 times negative 2 plus 4, and that would be 0 is equal to negative 4 plus 4, or, yep, sure enough, 0 is equal to 0. So that proves to be a solution for both of those, and that is the solution to the system. So as we work with writing a system of equations, that is where we have been practicing for weeks now, is being able to turn a sentence into a simple equation. And then, of course, we'll be able to graph that equation. So it reads that one satellite radio service charges $10 per month plus an activation fee of $20. And then it says a second service charges $11 per month plus an activation fee of $15. In what month was the cost of the service the same? Okay, Well, we are talking about cost, and we are talking about time, which is month. And we should be able to figure out that our cost is dependent on the month, or the amount of months, or the amount of time. So time would be our independent feature. So if we look at the first satellite radio service, so sat radio, and we know that that first one is going to be equal to, it said $10 per month, $10 per month, plus an activation fee of $20, plus $20. And the second one is going to be, the second sat radio is going to be $11 per month, and an activation fee of $15. All right, so looking at this, we can possibly come up with an equation. So let's go ahead and call the cost. The cost is going to be our output, which will be y, and the time, or month, our month will go ahead and be our input, or our x. So this first equation would be, we're looking at $10 per month plus $20. And the second equation is going to be $11 per month plus 15. So when we go to graph this, so if I go ahead and give some input outputs here, so as I input months into the first satellite radio station, I need to figure out what my cost is going to be. So as I do that, at 1 month, I know that I would go 10 times 1 plus 20, which is going to give me 30. So the first month is going to cost me 30. The second month is going to be 10 times $2. So that is going to give me $40. Third month, 10 times 3. Or let's do this. All right, so let's go ahead and input our months right into our equation. So we have 3 months is going to be 10 times 3 plus 20 is going to be 50. And 4 months is going to be 10 times 4 plus 20. It'll be 60. Starting to see our change, our rate of change here. And of course, 10 times 5 plus 20 is going to be 70. And 10 times 6 months plus $20 is going to give me 80. And I can go ahead and graph those on my coordinate plane over here. So I know when 1 month I'm going to come up here and I'm going to be $30. Month 2, I'm going to be $40. Month 3, 50. Month 4, 60. 5, 70, 80. And that is going to continue on for the duration of my service until I cancel it or they give me something for free, which is probably going to end up having to cancel first. So let's go ahead and look at the next satellite company. And as we put values of X in, the cost was determined to be 11 times the number of months plus 15. And then that will give us the corresponding output of our Y, which is going to be our cost. So we have 11 times some value plus 15. Okay, so go ahead and the first month, so it would be $11 times 1 plus 15 is going to give us 26. Then the second month, 11 times 2, which is 22. 22 plus 15 is going to be 37. The third month, 11 times 3 plus 15 is going to be 48. Let's see, continuing on, 11 times 4 months is going to be 44 plus 15, which is 59. 11 plus 5 is going to be 55 plus 15, which will give us 70. And then finally, $11 times 6 months plus 15 will give us 81. And I think we have calculated enough to go ahead and find that intersection point. But some of these are going to be a little bit off, because they're not right on our table. But let's see here, 26. 1 month and 26 is going to be approximately there. 2 months and 37 will be approximately there. 3 months and 48, right there. 4 months and 59. And then finally, we get really close here at 5 months and 70. All right, looks like we found an intersection point, and then it starts to get a little bit more costly. At 6 months, it's going to be about 81, and it's going to continue getting larger. So initially, the cost is a little bit less at $11 per month, but in the end, it will start to become, it breaks even. The costs are the same after 5 months, and then beyond 5 months, we should be able to look at that and say, well, satellite plan number 2 is more expensive after 5 months. And that's the kind of interpretation that you should be able to determine there, that satellite plan 1, until you reach 5 months, is cheaper. After 5 months, it looks like, because as we look at the graph, this is the break-even point. So from 1 to 5 months, satellite plan 2 is going to be cheaper. And then from 5 months to eternity, or, until the duration of your plan, satellite plan 2, or I'm sorry, 1 was going to be cheaper. So if I just accidentally said those backwards, my apologies, but satellite plan 2 is cheaper in the beginning, but then they get you in the end. Some of the and becoming more comfortable with it. So again, solutions of solving systems of linear equations by graphing. A solution is that overlap point where they connect and where they are both going to be solutions of each other. So, and we analyze those special solutions, identifying that parallel, infinite, or parallel no solutions, infinite solutions, or just a solution. So for graphing systems, we're going to talk about some special solutions here, and that is going to be infinitely many solutions or no solutions. So I'm just going to take a moment, and I'm going to go ahead and put in my coordinate planes. Okay, so looking here at A, it says, what is the solution of each system? Well, I can go ahead and just graph these independently, and I can turn around and say, let's see here, if I graph this first equation, I want to start it at the y-intercept, which is -3. So starting off at -3, and then I'm going to use the slope to calculate the equation. It's -1. So I'm going to go down 1 over 1, down 1 over 1, or I'm going to go back 1, up 1, back 1, up 1, and I'm going to graph that for the duration of my coordinate plane. And then if I go ahead and look at this other graph, so let me make sure I label this. I have y equals -x minus 3. And if I look here and I graph this next equation, which is going to be y equals -x plus 5. So again, going to the 5, and I'm going to do my slope, up 1, back 1, or down 1, forward. So graphing that equation, go ahead and tell you there's this graph, and it's going to be y equals -x plus 5. And what I know here is I can look at these two equations, depending on how you graph them, of course, and your accuracy. Those two equations will never touch. Because, one, if I look, they both have the same slope of m equals -1. So and they have different y-intercepts. This y-intercept is equal to, as we said, -3. This y-intercept is equal to 5. So they have the same slopes but different y-intercepts, so they will never touch. So there is no solution. There's no solution because they have the same slope. They're parallel, as we discovered earlier when talking about linear functions. And looking at this next one at B, Okay, well, B offhand in the form that is written in, if I'm looking for the solution, I can't necessarily graph this. So the first one, y equals 3x minus 3, I can graph that one. So let's see, right here, I know that the slope is equal to 3, and my y-intercept is equal to negative 3. So let's see here, negative 3, and a slope of 3. So I'm going to go up 3, 1, 2, 3 over 1, up 3 over 1, up 3 over 1, and I'm going to continue with that, and it looks something like that in my equation, and that is going to be y equals 3x minus 3. Now if I go ahead and convert this other equation to slope-intercept form so I can graph it, I'm going to begin by isolating it into slope-intercept form. So I'm going to go ahead and divide both sides by 3 so I can get y by itself. And that turns out that I have y is equal to 3x minus 3. And I can tell you what, look at those two equations are the same right here. So if I were to graph them, they would be graphed right on top of each other. Sorry. So these two equations, since they're identical, they have the same slope and the same y-intercept, they touch infinitely. So the same slope, same y-intercept, they have a continuous 100% they're connected, right? They have infinitely many solutions because they're the identical lines sitting on top of each other. So that's why they go on infinitely. They have the infinite solutions. And then here, just looking at these three examples of solutions, it says before graphing equations, how can you determine whether the system of equations has exactly one solution, infinite many solutions, or no solutions? Well, remember, if we have two lines, they will either be parallel, which means no solutions, or they will intersect, which means they have a solution. Now, if they intersect here, it just depends on if they intersect one time or if they intersect infinite many times. So one solution, they have different what to have one solution? Different slopes. They're going to intersect somewhere if they have different slopes of it in the equation. Now, over here, if they're parallel, so parallel lines have the same what? Or they have different y-intercepts, right? Different y-intercepts, but they have the same slope, because that's what makes them parallel. They will never touch for the same slope in different y-intercepts. And infinitely many solutions, they have the same slope and the same y-intercept because they are the same equation. So there you go, same slope, same y-intercept. And that's how you can quickly tell we're talking about solutions and how many there will be. So just keep that in mind. With this are going to be just recognizing it and getting it into a form like this equation right here, that we had to get it into a form where we were able to graph it. And as a class, we're going to practice more of that, but we've been doing this skill for many years. It was introduced to us in 7th and 8th grade, so we're just going to continue working with graphing.